Welcome everybody to our webinar. We'll be talking today about how we use in Scylla control theory to keep compactions under control. This goes a little bit deeper into the internals of Scylla, so I'm hoping you will enjoy it. I'm Glauber Costa. I'm the Vice President of Field Engineering at ScyllaDB. And for those who don't know us, ScyllaDB is the next generation NoSQL database. We are a drop-in API compatible replacement of Apache Cassandra, but with 10 times the performance and low and consistent tail latencies. Actually, some of the techniques that we're going to discuss here today are part of how we can achieve those results. We have open source and enterprise editions, and if you would like to know more, feel free to hit us on Slack or in the mailing list after the presentation. At this point, I would like to remind everyone that in November upcoming, 6 and 7, we're going to have our third Scylla Summit, and I would love to see you all there. Now let's talk a little bit about what compactions are, just so we understand and we're all on the same page about the background and what exactly we're talking here today. So when you send write requests to the database has to ingest those write requests. And to do that, we exercise a couple of code paths within the database. A write arrives and it's written to a commit log, so we can replay that later. We will ignore this for today. We're going to be talking about the path that happens here on the top. Those writes are accumulated in a structure called the mem table. It's a table that sits in memory. And every once in a while, according to some criteria, we will flush that mem table to an immutable structure called an SSTable. The SSTable, as I said, is a disk structure and it is immutable. And what that means is that although this is very fast for writes, when time comes for me to read that I have to consult those SSTables, those reads can be fairly slow. If I don't do anything about it, very soon we're going to be reading from hundreds or maybe thousands of SSTables. So it's a lot of disk bandwidth that is spent doing so. To help alleviate that, in the background, there is something called compactions that look at those SSTables, and according to a strategy, we'll talk more about strategy soon, decides to grab a couple of those SSTables, compact them together, merging the data, and then output one or more SSTables at the end. So this is called compaction, and it happens on the background. So in the general case, we have something that is happening in the foreground and something happening in the background. And control theory in Scylla helps us to deal with all of those background processes, not only compactions. We will be focusing on compactions today, but we have controllers for other things as well. So let's dive a little bit into what a compaction strategy is. Essentially, a compaction strategy tells us when to compact, which SSTables to bring back together, and how many SSTables and what is the shape and format of those SSTables will I have on the output. The goal of every compaction strategy is to reduce some form of amplification. Now there are many forms, many kinds of amplification, so let's go through which those are in the list in here. We can have read amplification, and read amplification is when I have to read essentially and effectively 1 byte of memory. I may have to go to disk, to the storage array, and fetch a lot more. So this is read amplification, and it happens when we have many different SSTables, because I will have to go and consult them, or I will have to dispatch a lot of I/O. So one goal of the compaction strategy could be, let's keep read amplification to a minimum. To do that, it may trade off space amplification. Space amplification is when I have a copy of the data many times on the storage array, or I have data that is no longer useful. It's already expired. I could get rid of that data, but for now, I'm keeping it on disk. So this is space amplification. And there is also the third case, which is write amplification, which is I'm writing the same data, I'm writing data relevant to the same key, time and time again into the storage array. So as I favor one of those amplifications, I may be sacrificing the other, which is why we have many compaction strategies. So let's take a look at the compaction strategies we support currently in Scylla. The main and the default compaction strategy is the size tier compaction strategy. So the size tier compaction strategy, what it does is that it waits for a couple it can be 2, 3, 4 that's configurable, or even more. It waits for some SSTables to be flushed together and picks the ones that are the same size. So what it tries to do is, like, if I have a write workload that is incoming, I will be generating a lot of SSTables that are relatively small. So I'll be packing them together. That means that I'll compact those more often. And in a second tier, I will have larger SSTables, and then I would compact them together when I have enough big SSTables as well. The level compaction strategy is a little bit different. It doesn't take into account the size of SSTables. It tries to reduce read amplification by keeping SSTables in a disjoint set in various levels. We're not going to be talking too much in details about level compaction strategy today. Another very interesting compaction strategy is the time window compaction strategy. And that is one compaction strategy that we usually recommend, for instance, for time series data. So what it does is that you can define a time window, say a minute, a month, or a couple of days, or whatever really you want. And every SSTable that is created within that time window is compacted together. SSTables created in different time windows are compacted separately. And what it allows me to do is that, for instance, if my data is TTL, I can just discard one SSTable without even looking at it, because I know that all of that data that was created together will TTL together. And last but not least, we have the manual compaction, or major compaction as it's called. This is a user-initiated process. You would be using the tool no2compact, for instance, and what it does is that compacts everything into the same SSTable. Now, we need to stop and try to understand what the same SSTable here means, and we'll talk about that in the next slide. So for those of you who are familiar already with Apache Cassandra, Scylla has some very important differences that I would like to cover now. The main difference between the Cassandra model and the Scylla model, and the way that affects compactions, is that in Scylla, all the data is sharded on the CPU level. So we have the token ranges that belongs to a node, but then those token ranges are split in smaller ranges, and then the data pertaining to those tokens are now split in the CPU level. So when we compact things together, it only makes sense for us to compact things that belong to the same CPU. That means that when you call a major compaction, that I just said that it's going to create one SSTable, what it really is doing is that it's creating one SSTable per CPU. I have no incentive, there is no benefit in joining together a file with data for multiple shards for multiple CPUs. So the result of that, for instance, is that if I have a system that has, let's say, for example, 64 CPUs, I will have 64 SSTables after that major compaction finishes. I would also usually have a lot of compactions per node. That is one of the reasons. And even when we're talking about level compaction strategy that has a fixed number of SSTables maximum per level, in reality, when I look into the shard, that invariant is kept. But when I look at the system as a whole, I usually have a lot more SSTables per each level. And that's why, because everything is sharded at the CPU level. Now, going a little bit deeper into what is the actual topic of the webinar, now that we understand and had a refresher about what compactions are, the big problem with compactions is that I have to figure out what is the best rate, what is the best speed for me to compact my data. If I do it too slow, I will be increasing read amplification a lot, and I will end up with a lot of SSTables that I have to read from, and my reads are going to be a lot slower. But if I compact too fast, my foreground workload will be disrupted, because I am now moving a lot of resources that could be used to process my requests to actually compact the data. So where is the sweet spot? One common solution is the one used by Apache Cassandra. It involves getting user-defined caps. So there's a throughput cap that I can assign to the compaction process. I can also do that to other processes like streaming as well. And I would just say, don't allow compactions to run at more than, say, 300 megabytes a second. I will instruct my compaction processes to go as fast as they can. But if they are pushing more than 300 megabytes a second, at that point, I will cap them. problem with this approach is like, first of all, how do I find that number? Who came up with the number 300 megabytes a second? Is it too much? Is it too little? So I have to go into a tuning cycle to figure out that. Not only this is costly, what happens if my workload changes or if I move to a bigger machine? Those numbers that work well before may not work well now. And also, what happens if I have a lot of idle time? Let's say that during the night, my servers are essentially idle. We see a lot of Scylla deployments with patterns like that, like temporal patterns over time. It works a lot from 8 to 6, but after 6 p.m., you don't have a lot of requests incoming, so I could be compacting at full speed at that time, but I am not because I'm capped at 300 megabytes a second. That number, of course, being an example. So we don't like this approach very much, and we never actually did this in Scylla from day one. What we did in Scylla in the past, before all of this work with the controllers was ready, is that I could, instead of defining maximum throughputs that I could achieve, I would define maximum ratios of resource usage. And what that means is that if I have idle resources, I can use them all. Because I'm not competing with anybody, and if I have more resources out of a sudden in my nodes, I will be able to use those extra resources because if I say let's just use 20%, 20% of more resources is automatically more resources. So it works a lot better than the throughput caps, but it still has some issues. And the issues with that is that there is no temporal knowledge, and I cannot make the decision with the static caps of go slower or faster now, so I can leave more resources or use more resources in the future. For instance, when the cluster is idle, I cannot make the decision of compact less now because I know that the cluster is going to be idle in the future, and then I can push the compactions to that future. So this figure shows us exactly what I'm talking about. And if you look here, this is Scylla 2.1 before all of this work was fully ready. And what we can see is that compactions are going to use a maximum ratio that I determined. It doesn't really matter what the ratio is. I mean, I think it was something like 50% in this example. That was also configurable just temporarily while we finished all the controllers. And what happens is that the impact of compactions is bounded. Compactions are not going to completely destroy and disrupt my foreground workload. But if you look at this graph carefully, what you're going to see is that there are times in which I'm compacting too fast and there's a valley in the workload. But then there are other times in which I'm not compacting at all. And if I look at the actual compaction graph that was obtained from running this workload, you can see exactly why. So this is a 3-node cluster ingesting heavy writes. And at times we are doing 30 compactions per node. This is a node with 30 CPUs, so every in most nodes are following this pattern. Almost every CPU is doing a compaction, but they finish too fast, and then I have that valley. But because they finish too fast, what I could do is I could make them slower, so they don't use a lot of resources, and they keep going until the next compaction is ready to start. So I never have this periods of valleys and peaks. So to solve that problem and to close that loop, we are using control theory, which is a strong mathematical foundation. It's used a lot in industrial controllers and in things like car cruise controls and other technologies. We're going to see some examples about what control theory is and how we can use that to leverage, how we can leverage that instrument to make compactions work better in Scylla and other databases. So a quick primer of what control theory is and how we go with using it. There are two kinds of control systems. So when I'm talking about control systems, I can be talking about open loop control systems. And an open loop control systems essentially has an input and I never look at the output. I never look at the state of the world, and it just outputs something that is proportional or some function of that input. One example is a toaster. So a toaster has a dial, and if I flip the dial to the right, I'm going to end up with darker toasts. If I set my dial a little bit more to the left, I'm going to end up with lighter toasts. That's a time dial. but I never actually looked. I mean, there is nothing really in this toaster that checks how dark the toast is at any point. It's just like, this is the input that I have, and then there's a proportional response that makes my toast lighter or darker, and I'll just trust that it's going to work. A washing machine is another example of something like that. You just define a time and let it run. And we actually have some open loop control systems inside Scylla as well. Heat weighted load balance, if you are familiar with some of the internals of Scylla, is actually one example of an open loop control system. But today we're going to be talking about closed loop control systems, which is what we use for compactions. So for closed loop control systems, we're going to be actually looking at the state of the system at any particular time. And we have a goal that we want that system to be, and we'll then just compare the current state to the goal state. The difference is called an error, and that error is fed back to the controller, which is why closed loop control systems are usually called feedback control loops. You might have heard this term in the past. So the goal of the controller is to move the system from far from the goal to a state that is as close as possible to our goal. One example of that is a water tank in an industrial controller. So you have basically a tank, and you have a particular level of water. You have a particular level that you want your water, actually, to be more accurate, any liquid you want that liquid to be. This might be actually just a level, a set line in the space, or it could be a range. For instance, if we're talking about a dam. In a dam, you don't want the dam to overflow, you don't want the water to go below the turbine levels, but you actually find for the water to be anywhere in between. It works like a reservoir. Then you have an actuator, and you have a transfer function, which is responsible to collect all this information and tell the actuator, should you open the valve more, or should you close the valve at this point, not to allow the water to flow. And actually, another interesting example is that we can actually turn an open loop control system into a closed loop control system by adding an element that looks in the world. So in the day and age of machine learning, one thing that we could do is that we could insert a camera inside the toaster, and that would look at this toast and say, hey, is it already at the darkness level that I want? And then I could actually come up with a toaster that is a closed loop, that is a feedback control system, by trying to keep the toaster on by more or less given the actual darkness that I see in the toast at a particular moment. Nobody came up with that idea yet, I believe. If somebody does, I'm pretty sure that's going to be connected to the internet. It's going to become an IoT device, and it's going to be yet another very interesting technology for us. So to summarize, there are three things that we need to do a closed loop control system. The first one is we need to measure the state of the world somehow. Then we need a transfer function that collects that information. What are my inputs? What is the current state of the world? Pass that to the transfer function and tell the actuator what to do. The actuator has the responsibility of enforcing some decision that the control system made into the world. I gave examples like of industrial controllers and water tanks and dams and etc. Let's see how that plugs into Scylla itself. So the first component of this is measuring. And to measure, we had to change Scylla. So we know at all times what is the state of every SSTable. And the SSTables, they can be in essentially a couple of states. The first one is the SSTable could be a partial SSTable undergoing a write. So what happens in that case is that I have something that was collecting, that was accumulating in a mem table, and now I'm writing it. That SSTable will become an actual SSTable of a certain size, but at any point in time, it is a partial SSTable. It's the one at the top, and it's being written. So I need to figure out that every time that I know, which is like currently every hundreds of milliseconds, what are the SSTables that are being written, and how much of that SSTable I wrote already. Then I have static SSTables, which are essentially SSTables that are just sitting there. They're not being compacted at the moment, and they are fully written. And there are also SSTables being compacted. SSTables being compacted, What that means is that I have to read through all of that SSTable. So to have a complete view of how my process is going, how fast my process is going, I need to know at any given point how much of an SSTable I have compacted already. So you can see here the two SSTables in the bottom. They're both being compacted. Let's assume together, but it doesn't have to be the case. And they're compacted at different rates, and they are in different points of that process. So I need to keep track of all of that. And as they are being compacted, they are also generated a new partial compacted SSTable that I also have to know, just like the first one, at which point of the process and how fast I'm going. Once I measure all that, I need an actuator. The actuator is the I/O scheduler, and those of you who are familiar with the Scylla architecture, you've probably seen this slide many times by now. What the I/O scheduler does is that when you install Scylla, we're going to benchmark your disk, and we're going to figure out exactly what is the sweet spot for concurrency for that disk. If I send less requests than that, your storage array will not hit max throughput. But if I send more requests than that sweet spot, I'm only introducing latencies. I cannot have more throughput. So what Scylla does is that the I/O scheduler intermediates all access to the storage array. I'll queue all the requests that are more. I'll send this maximum number of requests to the storage array, and I'll queue all the rest inside the database. I will now tag them. So I know exactly what of those I/O processes, what are those I/O's requests are coming from compactions. And the I/O scheduler works as the actuator. So if my transfer functions wants the compactions to go faster, I can increase the shares, I can increase the proportion of requests from compaction that I send down to disk. And if my transfer function, if my controller thinks that at this moment compactions should be slower, I can restrict that. It works as the engine in the water tank, and I say slow down. Instead of 10, only send maybe 2 or 3 requests that belong to compactions. And we don't have a slide for that, but in Scylla 2.2, not only we have an I/O scheduler, but we also have a CPU scheduler that does essentially the same thing. So if I have a lot of compaction requests, the CPU part of those requests are now also tagged. And if I want compactions to use 20% of the CPU, because that's what the controller determined, the CPU scheduler will be able to enforce that. So we now have measures, we know exactly the state of the world, and we have an entity, we have the actuator, which is the CPU scheduler and the I/O scheduler. They're able to look at the system and enforce the decision that the transfer function that the controller came up with. So let's look now at how the controller actually makes that decision. Well, what it does is that the first thing that we need to keep in mind is that there are many compaction strategies, and each of those compaction strategies, they will have a different transfer function. And we'll focus today on the size tier compaction strategy just because it's widely used and relatively easy to understand. The reason that different compaction strategies have different transfer functions is that my transfer function, the transfer function that we chose to use in Scylla, has to measure something that we call the backlog. The backlog is how much work, is an estimate of how much work I still have to do to move the system from the current state to my desired goal. So remember, the closed loop control system always have a goal that I have to get to. So the goal is achieve a state where there is no amplification whatsoever. So for the case of size tier, what that means is that everything is sitting on a single SSTable. So there's no space amplification because all the data is already deduplicated. There is no write amplification at the moment because we have a single SSTable, and there is no read amplification. There is a single SSTable and we're reading everything from it. Just a quick reminder again, this is all per shard. So what I have to figure out is from the current state that I am at right now with all the SSTables that I have in the system, how much work do I still have to do to reach that magic state in which there is no more amplification in the system? For the time window compaction strategy, just as a quick example, that magical state of no backlog is the state where I have a single SSTable at most. I could have 0, but at most 1 per time window that I have determined for the current time window and for all time windows in the past. And the controller output, once I determine the backlog is the hard part, but once I come up with that, I can just use a proportional function. And the reason I can use a proportional function is because this becomes a self-regulating system. And it's not that hard to see why. When I have more compaction shares, what happens is that I have less new writes because compactions are now using more resources. The new incoming writes now have less resources to work with. They become slower and they generate less compaction backlog in the future. And the converse is also true. If I have less compaction shares, I will have more writes, and as a result, more compaction backlog. So this is a kind of homeostasis system in which at some point I expect to reach an equilibrium. So what we're going to end up with is that we're not going to be in the state of zero backlog necessarily when there is incoming writes, but I'll keep increasing my shares or decreasing my shares until that reaches a perfect equilibrium and my system is stable. So I said we're going to focus today on the size tier backlog example. How do we come up with that backlog? So let's just take a quick primer again on how size tier SSTables are organized together. We can have a write in progress, which is an SSTable that has been written at this moment, and it has a certain size. It will have a certain size X in the future or close to X. So when that lands in my system, I will look and I'll see that I have another SSTable that also has the same size or about the same size, and I'll compact them together into a new SSTable that is going to be roughly twice as big. And then I will find another SSTable that is also about the same size, and I'll compact them together, creating a new SSTable that is now roughly 4 times the size. So that is essentially how size tier works, and each of those sizes that are close to each other but far apart from themselves are called tiers. So I have many tiers depending on the size. That's why it's called size tier. So the realization that we need to calculate the backlog for size tier is that each byte that it's written now, so if I'm flushing a byte now at this very moment, I will have to rewrite that. So I have to do that work again. A number of times there is proportional to the tier, the difference between my current tier and the maximum tier in the system. So to make that clear, if I have 2 tiers in the systems, like the example we saw before, and I'm writing a byte now, I know that I will have to write that byte again 2 times to reach that state. And the tiers, they're proportional, as the name implies, to the size of the SSTables, and more accurately, to the ratio between the size of the entire table, which is the sum of all the SSTables, and the current table. Let's try to put this in numbers so we understand this a little bit better and see some numerical examples. So let's say, for instance, that I have 4 SSTables in the first tier, that each of them have just 1 gigabyte. And then I have a second tier with SSTables that are now 4 gigabytes. So you see that they live in a different tier. They are clearly in the tier above my first tier. The total size for that table is 20 gigabytes. So if I take the log of that ratio, then what that gives me is essentially the number of hops that I have to take, that difference that I want between my current tier and the last tier in the size tier system. So to look at the numerical example, if I have 20 gigs total, each SSTable of size 1 gig, if I take the log, and I'm just using base 4 here because we usually compact 4 SSTables together. That's not a requirement. And if we get this wrong, we're going to be wrong by a constant factor, which is still fine. So what I end up with here is that the log 4 of 20 over 1 is around 2. But when I look at the second tier, 20 over 4, log 4 of that is around 1. So what that means is that I will only have to copy all of those bytes and rewrite them and read them and write them again another time. So they reach the state of 0 backlog. And what happens, for instance, if I'm already in the state that I have a single SSTable in the system, that SSTable would be, in this case, 20 gigabytes. 20 over 20, the log of that is 1, the log of that is 0. That means I don't have any more backlog. So that's how the size tier backlog works. And as I said, I mean, we've been calculating the cost of writing, what's the cost of moving every single byte from the current state that they are to the last tier. So the backlog for one SSTable is just the size of that SSTable, because I'm gonna have to do that for every byte times that thing that we just discussed, this log factor. And then the size of the entire table is just the sum of the backlogs for all SSTables. So what is the amount of work that I have to do to move that all into the state of zero backlog? Let's now finally look at some examples of how that works in practice. And if you are curious to know more, we have recently published a blog about it, and you have all of those, most of those graphs in the blog, and also more detailed explanation with more math, with more formulas about how the whole backlog calculation works. The graph on top we've already seen earlier in the presentation. Is essentially the first throughput graph, the equivalent compaction, the number of compaction graphs. So you see that at some point I'm compacting 30 SSTables in the entire system, and then I'm not compacting anything because I compacted that way too fast. It disrupted my workload too much. Then I don't do anything for a while, and then I compact a lot more for another while, and you keep having the system with those disruptions. So this is 2.1. When you look at 2.2, which is the graph on the bottom, when the controllers are all finally ready and for size tier, and I can control automatically the compactions with size tier, what we see is a graph of compactions that is a lot smoother. So I'm not going to go too fast in the beginning because I know that my backlog is still under control. It is still at a constant rate, and then I can just slow them down and decide to use more resources in the future. So I'm equalizing those things over time. And when I look at the throughput versus CPU utilization, what you can see here, if I focus, this is focusing the previous workload in a single CPU. So the green line here is the throughput of the system. You can see that it starts relatively high because I have no compactions that are going on at this moment. And then the percentage of CPU, and I'm focusing on CPU here, it could have been the disk, but this workload happens to be CPU bound. So I'm looking at the percentage of time that is off the CPU that is used for compactions. And it keeps growing. In the beginning, it's 0 because I'm not compacting anything. And it keeps growing, growing, growing until I reach that state of equilibrium that I discussed in the past. In this case, we are using around 15% of the CPU dedicated for compactions, but it's 15% all the time. And you don't see those oscillations. The throughput is also fairly constant. But that is a little bit boring because you can also, if you have lots of time and if you have lots of experience, you can also, for this workload, find that magic number, find the throughput cap, or even the ratio, let's say in this case 15%, that make my compactions go at the perfect speed. It's hard to get those things right, but let's assume you were really good at it and you can still do it. Things get a lot more interesting when this workload changes. So I'm simulating a change in this workload. I've been writing payloads here that are 1 kilobyte in size. And what happens if out of a sudden I increase the payload, I make my messages bigger? So what I expect to happen is that I have less throughput because each write is now more expensive, so I can do less of those more expensive writes. I also expect my backlog to grow faster because I'm ingesting more data at once in that formula, the part that has to multiply the number of bytes per the log factor. So let's see how the controller responds to that, which is the part that is hard to do manually in a system. So as you can see here, this is the same graph that we saw before, but instead of capping it at time, I am now letting the graph go a little bit further. And what we see is that there's going to be some disruption when the workload changes, but very soon things get smooth again. This is the controller automatically finding the new point, the new ideal point to run the system. This is all automatic. There is no manual. There is nothing that you need to do, seriously. So if you're thinking from the perspective of a Scylla user, all you need to do is sit down, relax, and look at your graphs, and you're going to see that the compactions are now finding the new state where the backlog reaches an equilibrium. Although it's not the main goal, we can also look at the latencies and what happens with the latencies. Because I'm doing those things at constant ratios, I should expect the latencies to be fairly constant at the output as well. So when we look here, for instance, at the example, you can clearly see where's the disruption point. You can see that before that disruption point, I had the 95 percentile latencies. They are the green line. They are around 1 millisecond for this workload. They keep being around a millisecond, albeit a little bit higher after the disruption, but they're still fairly bounded. The 95 percentile jumps after the disruption because now the payload is bigger, but it also moves in a very predictable way to around 2 milliseconds. And the 99.9, it follows the same pattern, it follows the same movement. I mean, there is a disruption, it gets a little bit higher, but everything is still bounded. And that is just a new reality for this new workload. So that's what I had for today. We'll take questions now, but before that, I would like to thank you all very much for attending the webinar. And I'll remind you again that November 6th and 7th, we will have the Scylla Summit in Redwood City, close to San Francisco. Before, in the first day, the 5th of November, we're gonna have training. So the registration is already online. And if you have a nice thing that you're doing with Scylla and you would like to present at the Scylla Summit, you're also going to be very welcome. The call for papers is already open. We already received some presentations, some of them actually from some of you that I can see in the attendees list. So keep them coming, and hope to see you at the Scylla Summit. So I'll take questions now. Let's see, we have some of them here. All right, so I'll answer this. So the question is, we process 300 million users' data using Spark and write them to ScyllaDB. The total data size is 300 gigabytes. We use an M4 instance and have the concurrent compactors at 16. So I'll read the full question later, but let me just pause here. Because Scylla is auto-tuned, we always ignore current compactors. We really never had that. We parse that because it's part of the Cassandra file, and we want to provide like seamless migration path. So we will read all of those options, but a lot of them we just ignore, just because we are going to be auto-tuning these things. They're not led to the user using technologies like the one we saw today. But moving on with the question, while the write happens, there will be read as well by other APIs. Sometimes I see read timeout, read timeout. What compaction strategy is being used? I don't see a strategy set in Scylla.yaml. So it's very hard, of course, to debug a system during a webinar. I don't know why you have read timeouts, although from our experience with Spark, there are a bunch of stuff that comes to mind. I would recommend to join our Slack channel, talk to us. We're always more than happy to help. But the core of your question, the strategy is a property of the table. So when you create the table, you can define a compaction strategy. That's nothing the Scylla YAML, and you can have in the system different tables with different compaction strategies, right? So it depends on the write patterns, the access patterns of that table. You would essentially want different compaction strategies. So, okay, so that was done. So there is another one here. How does the backlog work for a time window compaction strategy? Let's answer that live. That's also an interesting question. So the way it works is like what time window compaction strategy does is that it separates, as I mentioned before, it separates the data in time buckets. So those time buckets are different, and things are put in buckets according to the timestamp of when they were written. So I want those, and inside that bucket, what I'm going to do is that I'll keep performing size tiered until that bucket is in the past. And when that bucket is in the past, I'll do a major compaction in the bucket. So I'll be left with a single SSTable per bucket. So the backlog really is exactly like the size tier backlog. The only difference is that instead of summing all of the SSTables in the entire table, I'll just sum all of the SSTables in the bucket, and then I'll sum the buckets together. So that's essentially what the time window compaction strategy backlog is, because time window is just size tier, but it's split in different buckets. So all I have to do is consider those buckets separately. Done. So there is another one. Are there other use cases for control theory in Scylla as well, or just compactions? There are plenty. So we chose to focus on compactions because it's one of the most complex examples, and it's one of the things that users complain about the most. which is very hard to come up. And some users had said to me in the past, especially the ones with some experience with Cassandra, we are outright afraid of compactions. When we run compactions, the workload is disrupted a lot. So that's why we focus on those explanations in compactions. But another thing that is controlled is the flushes from mem tables to the disk to the storage array themselves. This is also controlled. And we also have open loop control systems, as I mentioned, heat weight load balancing, which is the component in Scylla that distribute reads to different replicas according to their cache hit ratios. That is also a control system, although an open loop control system, and we use control theory there as well. Okay, so those are the 3 questions that I had at this point, and there's another one. Yeah. So yeah, we're doing live debugging. I have a size tier compaction strategy on a table that store time series data. Is it a good idea to set the strategy at time window compaction strategy? That's also a good question. So the answer is depends. It usually is for time series, but the biggest appeal of time window compaction strategy is that data TTLs about at the same time. So if you have TTLs in your data and you have time series data, for sure it's a good idea to switch to time window. If you don't have TTLs, then it is a little bit more complex. I would invite you to discuss that in more details with us. He has TTL, so yeah, it's a great idea to use time window. And that is controlled. Time window compaction strategy is not a control compaction strategy in Scylla 2.2. It will be a control compaction strategy in Scylla 2.3. Done. All right, so let's see if more questions pop up. All right. So it seems like we don't have any more questions. I would like to, at this point, thank you all for attending the webinar, and I hope to see you in November at the Scylla Summit. Thanks, Pat. Thanks, folks.